Alright, I'll just wait a few more minutes, let some people get in, and then we can get started. Alright, let's get right into it then. Alright, hi guys, my name's AJ. This will be a cumulative review of the general chemistry portion of the MCAT. This is dedicated to all the test takers taking the exam on April 9th. I'm getting this out to you as quickly as I could. You might have noticed I took like a small break between my live streams. That's because I wanted to redo my curriculum. I wanted to make sure that I can get the material out in an efficient way. So I redid it a little bit. I'll be doing general chemistry today and a little bit of the math that will be present. And tomorrow I'll be doing organic chemistry and a little bit of physics. Not a lot of stuff I need to cover in physics. It's mostly equations, so it'll just be like a little bit of that. Alright, with that being said, let's just jump right into it. Let's start with the basics of chemistry. I think we are all pretty familiar with how chemistry works, or like the basics at least, when it comes to periodic trends and all that stuff, but I'll jump into it anyways. We'll start with specifically the periodic table. Actually, I'll change the color. Let's do blue. Awesome. So we know, I'll start off with atomic radius. So atomic radius, we know that the trend is down and to the left. This is the only trend that goes that way. So atomic radius goes down and to the left. Actually, I think it'll be confusing if I do it like that. Let me put everything like here. So down to the left, we'll see that's atomic radius. Next up, let's go with ionization energy. Ionization energy, it's a complete opposite. It's up and to the right. It's not just ionization energy though, guys. It's also electronegativity, electron affinity, ionization. I already said ionization energy. I was thinking of the effective charge. All right. I believe that is all the atomic or like the periodic trends you need to know. These are easy questions. I think like these aren't hard to memorize. You can just go ahead and like if you have your own periodic table printed out, you can just write down on yourself. I would have written it here, but it would have been really confusing. But yeah, these are super easy concepts. Just memorize it, you'll be fine. I'm gonna change back to white. Actually, no, I'm going to change it to red because I have some more stuff I want to talk specifically about this. Let's talk about what the different categories are in the periodic table. So it says right here the rows are groups, the columns are groups, the rows are periods. That's pretty obvious. Note that the reds are metals. Or actually, these are all metals. So all of these are metals. And these, moving forward, are non-metals. Actually, no, that's still pretty confusing. I'll write it up here. I'm trying to think of like, I would highlight the metalloids actually. So it's something like this, I believe. Here. These are all the metalloids. Everything to the right of it are considered non-metals. Everything to the left of it are considered metals. That's the clearest I can make with the periodic table I have here. You guys know the concepts behind metals, non-metals, metalloids. Metals are solid, lustrous, good conductors, stuff like that. Non-metals are the opposite. Metalloids, they have in-between properties. Like high school chemistry stuff, you should be fine with that. I'm just gonna jump right into like exactly why these are like colored differently. So the reds are we're talking about orbitals here. Yeah, so the reds, these will be in the s orbital. The yellows, these will be in the p orbitals. Blues, yeah, I probably shouldn't have switched to white. D orbital, I'll change that to red. And these guys right here, they're actually the f orbital. You'll never get tested on anything about the f orbitals. It's just good to know that there are like these are the ones that will be present in the f orbitals. And note that the top ones, these guys, these are known as the lactinide series, and the bottom ones, these guys, these are known as the actinide series. They're both like metals, they're just incredibly rare. Like I said, you won't get tested on that, just know what they're called. With that said, I would want to move on to, let's talk about atomic weight, atomic mass, what like these numbers are exactly. So I'll start right here. So can somebody give me an element? Is there any element that you guys want to know? Let's do carbon, sure. So carbon, so yeah, with that, let's talk about what this number is. This number is the mass number. The mass number is the mass of the atom, or sorry, the molecule. Atom, yes. It's the mass of the atom in AMUs. So that will be the addition of protons as well as neutrons. So with carbon, it has 6 protons, 6 neutrons, so it'll be 12 total. That being said, this right here is the atomic number. That would just be protons. Also will be the number of electrons, as they will be equal to each other, as you guys know. Memorizing like which one is which, I just like to think mass number is more massive, so the larger number will always be on top. That works for me. If you guys have anything else, feel free to use that. You guys know Avogadro's number, right? I don't have to cover that. Atomic weight, I'd want to cover. And that's important for stuff like isotopes. It's basically just the average of all the masses of the isotopes. So average of all isotopes form the atomic weight. Let's talk about Planck's quantum energy. Actually, I won't cover quantum theory just yet. I'll talk about the Bohr model first. So you guys are familiar with the Bohr model. Let's talk about this. If an electron is being pushed outwards like this, it's absorbed. That's one thing I'd want to get through to you guys. If it's going out, it's being absorbed. If it's going in like this, it's being emitted. I've gotten this question wrong so many times. I don't want you guys getting this wrong in test day. Know that if it's going out, it's being absorbed. It's going in, it's being emitted. Delta E equals HV. That's Planck right there. It's a pretty easy equation for you guys to memorize. Just remember that that delta E equals HV can also be changed or like manipulated to be delta E equals HC over delta. Oh, sorry, I'm thinking about something completely different here. But no, this, I'm thinking about a different concept. It was be HF. It should be HF here too. I'm not sure why. But anyways, if it's delta E equals HF, you can derive it or manipulate it so that it's delta E equals HC over lambda, which is wavelength. C is the speed of light, which is 3 times 10 to the 8th meters per second. Yeah, that's pretty obvious. They'll never give it to you like this. It's just too easy to plug in. You'll have to know that you have to derive it like this. So yeah, that's pretty much all I can talk about with Bohr's model here. I think like knowing the difference between energies from like n equals 1 to n equals 2, you'll have an equation that's like set up so like E equals negative R H over n squared, and like you'll have to find the change in energy. It'll be like you just plug it in like R H over n. What? Let me get some more room here. So it's like, yeah, delta E equals RH 1 over N1 squared. This will be like N1 initial. So I'll make this look like a 1 initial. So 1 over N1 final. So yeah, it'll be something like that. Let's move on to quantum theory. We'll talk about quantum numbers. That's also something that you guys should be familiar with. You should know what it's all about. So the principal quantum number, it's your first one, symbol N. It's any integer value. Know that it's what it represents is the character of the or sorry, not the character. They all technically represent the character. They represent the specific shell. So the quantum number will be like S, P, D, stuff like that. The angular momentum quantum number, L, it's any integer as well, but it's n minus 1. So if you have, if your n value is 4, your L value will be 3. It represents the subshell that's present in. So if it's like S1 or S2, it's something like that. Magnetic quantum number, M sub L. It's any value from negative L to positive L. Still will be integers. It represents the orbital that the electron is in. And the spin quantum number represents the spin value of the electron. It'll always either be positive or negative 1/2. That goes into, I want to talk about the Heisenberg uncertainty principle. So I'll just write Heisenberg here. We can just talk about this. The Heisenberg uncertainty principle states that like you do not know the exact location and the exact like spin, or not the exact like charge of an electron in an atom. It's completely uncertain. You just have to work with probability. That's why it's so important to know about the spin value. This ties in with the Heisenberg uncertainty principle. I want to talk about the alpha principle. It's the way that you fill it out. I'm gonna need a lot more space. I thought I would need to be here. Let me write like on top of this actually. So it's like Actually, no, I don't want to write that. It's going to be too messy. But the gist of it is that when you start off at 1s, you go to 2s, and then you go to 2p. And 3s, 3p, 3d. It's not as messy as I thought. I'll just go with it. So yeah, I'll start off like that. With 1s, you go down like this, 2s, 1s, 2s, 2p, 3s, 3p, 4s, and then you go to 3d, and you fill out 4p and 4d. So just know it's like a zigzag pattern with the off-ball principle. Next, let's talk about Hund's rule. Hello? Alright, sweet. Let's talk about Hund's rule. So Hund's rule states that with any given subshell, orbitals that are filled, they will go to the maximum number first. So it's like, so I'll do 1s, 2s, there shouldn't be something here. Where's the eraser? So I'll start off here. So when you're filling out an orbital, you'll go like this, right? And then same thing with 2s. But if you're filling out an outer orbital like this, you would not go like this, but instead you'll be filling out every orbital and then you move forward. So it'll be like that. You guys know what valence electrons is. I don't think I need to talk about that. Is there anything else that you guys want to talk about, which is like specifically like basic chemistry, like high school stuff that you guys might have forgotten about, like Avogadro's number? You guys know that, so like I'm just saying, like anything else on the lines of that. Because like if not, we can move on to bonding. Any questions? All right, cool. So with bonding, well, first off, like, is anyone confused about the octet rule? Let me see if you guys have anything confused with the octet rule. I don't think you guys are confused because like it's pretty straightforward. Just like you know that there's like more exceptions than there are like things following it. So I think we're fine with the octet rule. Should I move on to Lewis structures? Do you guys want Lewis structures or formal charge first? All right, I'll start off with Lewis structures. So the steps for writing a Lewis structure, so you start off with let's use a HCN. You'll use like the obvious, this is step 1, you just write it out. Step 2, let's count all the valence electrons that are present. So hydrogen, there's 2. Nitrogen, how many is there? There's 5. Carbon, there's 4, I believe. 4, yeah, 4. So then now we just start writing let me count valence electrons. Now 3, let's see. I'll erase formal charge for a second so I can have more room. 3, now we draw all the single bonds. So now next step up 4 is completing all the octets. So let's start with nitrogen, let's fill that out. And then step 5, we need to replace extra electrons on the central atom. So you see that carbon doesn't have its octet filled, right? So we want to get this to 8. The way we do this is we move these 2 lone pairs here so we can fill everything out. And this is actually right. This is exactly what hydrogen cyanide looks like. So these are the 4 steps that you need to take. Just start with I just realized these are the exact same. Write skeletal structure. Draw single bonds between the structures. So focus on the central atom, all right. All right, so with that said, let's move on to a formal charge. You guys are familiar with formal charge. It's you guys are, like, have probably always heard it as like dots versus sticks. That's how I've heard of it anyways. So it's like, so the formal charge equation is valence electrons minus dots plus sticks. I don't know why, but like in element or like in high school or college, this is always something that like tripped me up because no teacher really explained it as dots plus sticks. So it's, you count the individual dots. So like this would be 1, 2, but with sticks it just counts as 1. So let's see the formal charge on this carbon right here, for example. We'll do it in red, or let's do it in blue. So starting off with the valence electrons of carbon, what is that? 4, right? So 4 minus dots minus sticks. So 1, 2, 3, 4 dots, or 4 sticks, sorry. It's 4. There's no dots around it, so this will be 0. That's perfect because once you get it to 0, it means it's like completely neutralized. It's preferred. It's in the preferred structure, the preferred resonance structure. You don't want a negative value on or if you do have a negative value, you'd want it on the most electronegative atom, or most electronegative element. Which one's the most electronegative element here? You're gonna have to look at your periodic table, but this will be nitrogen. And as you can see right here, it's 5 minus, what is it, 1, 2, 3, 1, 2. Well, it's actually also 0 here. But if we had a negative charge, it would be preferred to keep it on the nitrogen. So yeah, let's move forward. Is anyone confused about polarity? I have a picture of it here. And essentially, the gist of it is that you have partial positive charges on some atoms, but you have partial negatives on some other atoms. So that's way the way bonding works is that you just they're attracted to each other. So I'm just trying to think about that. The biggest thing I want to talk about bonding would be IMFs. Anyone confused about polarity though? I don't mean to like rush through this or anything. Not seeing anything in chat, so I think you guys are good. I'm sorry, I'm just looking through my notes because I want to make sure that I have the exact same picture present for something else right here. So now that we covered that, let's talk about intermolecular forces. So ionic bonding versus covalent bonding. Do you guys know the difference? Let's think of ionic as metal to non-metal. And covalent, yes, I'll just do non-metal. Okay, cool. I thought I was muted for a second, I'm sorry. Yeah, no, if I went through all that and I was muted, I don't know what I would do. That would be really embarrassing. So yeah, non-metal versus to non-metal. Ionic is metal to non-metal. Metallic bonding, it's pretty obvious what that is. It's metal to metal. So with that being said, let's just jump right into, let's talk about covalent bonding really quick. So there is polar covalent and non-polar covalent. So I want to stress this about ionic and covalent. The way you distinguish them when you're not given enough information is electronegativities. So if you're given an electronegativity that is less than 0.5, this will be a nonpolar covalent molecule. If it's greater than, I believe 1.7, I think for the MCAT it's 1.7, you will be going into ionic territory. It'll be an ionic bond, metal, non-metal. But if it's between those numbers, so let's say X is greater than 0.5, but less than 1.7, I'll highlight this so there's some more clarity. That would mean that it will be polar covalent. So yeah, make sure you memorize these numbers. They're very important. So moving forward with that, let's jump into intermolecular forces. It's like the beef of all this bonding material. Let's start off with the weakest, London dispersion forces. It's basically sort of like polarity. It's more like you're just like finding like, it's like rapidly changing like dipole moments. Very small dipole moments though. So this is present in every molecule, or almost every molecule. For the MCAT, it'll be present in every molecule. This is basically the backbone of bonding. So everything has it. If you're ever completely confused about a question about bonding, they're asking something along the lines of what kind of bonding this is, just choose London dispersion forces. You're probably going to be right, because like I said, it's always there. Dipole-induced dipole and ion-induced dipole, these go into polarity stuff. It's definitely just like which one is pulling towards a positive charge, or which charge is pulling towards like negative charges and all that. So these, I just want to say, like, this is in ascending order of strength. So ion dipole is the strongest, and London dispersion forces is the weakest. Like I said, ion dipole, these would be your ionic bonds, your metallic bonds. So that's why these are also very strong. Covalent bonds are relatively weaker. Dipole, I just covered that. Hydrogen bonding is something really important because it is very specific. It's also very strong. It forms the backbone of a lot of like our amino acids, our major biomolecules. So I just want to highlight that. I want to focus specifically on it bonds to these three molecules. Hydrogen bonding is fun, guys, right? It's fun. Fluorine, oxygen, fluorine, oxygen, nitrogen. These three are the ones that it bonds to. If you ever see like a hydrogen bonding to one of these, just you make sure you know that it is a hydrogen bond. All right, with that being done, let's move on to Vesper. I'm not a huge fan of Vesper. I've always struggled with it. But that being said, I love this chart. This is my favorite chart in all of like studying for the MCAT because it got Vesper into my head. This is great for like all the geometry. It covers basically everything. Like even like stuff like T-shaped, like I never learned about T-shaped in high school or college, but they got it. You just memorize this chart, you're fine. So if you see like there are, like if there's 6 groups, there's no lone pairs, you'll know it's octahedral. 5 groups, there's 1 lone pair, seesaw. So yeah, just memorize this. Feel free to screenshot this. I'll wait on this for a little bit. With that, I'll be moving forward with gases. Or not gas, I'll be moving forward with stoichiometry, sorry. Everyone got this screenshotted? Sweet. So with stoichiometry, I think it's pretty like self-explanatory. Yeah, no, I'm sorry. My notes are like sort of like meshing forward. It's really hard to do it with like a whiteboard like this. But yeah, so I think it's you guys know what your moles are, you know your formula weights, molar masses, stuff like that. So let's do like a multiple choice quiz real quick, actually. I want you guys to write in chat what you guys think these mean, or like what the skeleton equation for these are. I'll write this smaller and a bit more like clearer. I know I'm like sort of like moving forward to the top like that. Sorry, but I'm trying to fit this last one in though. Alright, cool. So, with that being all said and done, let's talk about this. You guys got anything to say? Which one is which? Can somebody say something about a combustion for me? Right. It's basically any carbon stuff. It's basically just, I'll use methane for this example, plus let's say like oxygen, so 2O2. Yeah, I think it's right. So I'll yield CO2 plus O2. It's important to note that this and this will always be there. I'll circle these for the other ones too, because you need to know that these are the important reaction like constants for these. You're always gonna form You're always gonna form a carbon dioxide and an oxygen. So with combination, it's basically just A plus B forms AB. That's exactly what you think it is. Decomposition, yep, it's the complete opposite. Single displacement, A plus BC. Equals B plus AC. Straightforward. Double displacement. So, sorry. CB plus AD. And neutralization, this is something you guys probably don't know, right? I didn't see a lot of people answering the neutralization question. Yeah, I've seen one person, you just said it was like it ends with salt and water. You're kind of right. You mean you are right. So it's like, whatever you have here, just know that you're going to end up with something like NaCl. I'll just write salt plus water. Yeah, sorry, I can't think of like a specific a specific example right now. It'll always be a salt, and there's always going to be a water. That's neutralization. This is very important for acid base chemistry. So if you want to like take a note of that, make sure you remember that. Combustion, that's also very important. You're probably going to get a question about combustion. These, like, they're all like pretty straightforward high school chemistry level stuff, but know them anyway just to be safe. Stoichiometry, dimensional analysis, you guys know that stuff, right? I'm trying to think of something that it's basically math. I'm not really sure how I can teach it to you. You just need to know how to practice it. All right, cool. So let's move on to kinetics. I love kinetics. It's a lot easier than a lot of other stuff in Gen Chem. Kinetics and equilibrium, like that's my jam right there. So you guys know like how like the charts for kinetics look, right? Whoops. I'm getting rid of this for a second. I'll talk about KQ in a second, but the gist of it is like This is your free energy, and this is your reaction coordinate. So you guys know that this right here, do it in red, this big bump right here, that's your activation energy, and you know that the rest of what we have here from the bottom of this part, that is your delta G. So I want to point out that delta G is products minus reactants minus products. It's easier to well, I'll be getting into this later, obviously, but like you'll be thinking of a lot of stuff in products minus reactants, but in order to get like an actual value for this, you'll be thinking of it in reactants minus products, if that makes sense. So I'll write this for now as reactants minus products, but know that it is like in the future you'll be thinking of it a lot differently. In the future, basically an hour, but let's just bear with me, all right? So with that being said, let's talk about how equilibrium constants work. I have a basic like skeleton equation written right here. So these right here, these are your reactants, and these right here are products. So these are coefficients of reactants. So like if you have like two, like oxygen, the lowercase a would be the 2, the a would be the oxygen, so forth like that. Your Kc, that's your equilibrium constant for a kinetic equation. It'll always be products over reactants, and the reactants, products, both of them, they'll always be raised to their coefficient. So it's, if you have 2, it's not you're multiplying it by 2, you're raising it to 2. It'll be squared, not times 2. So yeah, I want to talk about KEQ. I had that written down. Let's talk about it for a second. It's your equilibrium constant. So when assuming everything is at equilibrium, it will equal that certain number. So I want to say, if equilibrium, you're thinking like it'll be products equals reactants. That's not necessarily the case, because if that was true, you'd always get 1 as your KEQ, right? So it's actually, it'll be preferred in a different way. So if KEQ, I'll write KEQ. I'm not gonna be lazy about this. KEQ, if it's greater than 1, what does that mean? KEQ is greater than 1, so it's products over reactants. So what does it mean if KEQ is greater than 1? Exactly. You have more products. So if you have more products, this would be great to go into Le Chatelier's. So you have more products. I'll also write that as more products. If KQ is equal to 1, we just talked about this. Products equal reactants. Very rare to see this. Like I'm thinking like just in general, I don't think you'll ever see this. I've never seen this in like my labs or anything like that. KEQ being less than 1, that means you have more reactants. Now, with that said, let's move on to Le Chatelier's principle. I love Le Chatelier's principle, man. It's just such like an easy thing to memorize, and it's so easy to like think about in concept. So, do you like Le Chatelier's principle too? Yeah, let's go, baby. A plus B. I'm thinking of like an easy way to think about this. Equals like whatever product. So let's say C. So if you add more of a reactant, so let's say there's more of A. If you increase A, you're adding more onto one side. And if you're adding more stress onto one side of the reaction, you have to push it this way. So if you're adding more of A or B, you're leading to a right shift. Likewise, if you're adding more of a product, you'll be shifting it to the left. if there's pressure applied, if you're adding pressure to the system, so let's say if you're adding pressure or if you're lowering the volume, it goes down, or it goes to the right, so it's a shift right. And likewise, if you're lowering it or increasing volume, shift left. Now, I talked about pressure, I talked about volume, I talked about the reactants. So let's talk about heat. Where would that be? What would temperature play a role? Is temperature a reactant? Close. It's actually, I guess it depends. Depending on if it's endothermic or exothermic, it will either be a reactant or a product. So I'm just going to say heat is an equation. So if it's exothermic, heat is being released, right? So that means heat is being produced. So it will be present here. So if you're adding more heat into the system, you'll have to you're adding it as a reactant here. So you'll be shifting it to the left. But if it's an endothermic, it'll be adding heat here. It'll be shifting it to the right. So yeah, I think that's pretty much all I can talk about with Le Chatelier's principle. I wish everything else on the MCAT was as easy as that, but I can dream, right? So super easy concept. Make sure you memorize that. I think all of kinetics is also pretty straightforward. KEQ. I saw somebody said something about a Q and KEQ. I'll talk about Q in a second, but Q is yeah, I'll just add it here. Q is basically the equilibrium constant where Q is basically the equilibrium constant when you're not in equilibrium. So at equilibrium, you'll be using KQ, but without equilibrium, you'll be using Q. Got it? Cool. Let's see how much. I'm trying to make sure that I'm not like breezing by this. I want to make sure that you guys are understanding what's going on. Man, I'm always taking up so much space. Let me thermochemistry. Yeah, I guess it's just the water. Let me erase that for a sec. You guys are never going to see this, but I'm going to write it anyway just for myself. Yes, sorry, I need to recalibrate my board or whatever. It's a bit weird. All right, so thermochemistry. Who wants to enlighten me on this? Sweet. That was weird. What is Q equals MCAT? We'll get there. Let's talk about systems first. So I'll write these down really quick, and I'll read them out to you in a second. We talked about exo and endo. I think we're fine on that. So let's talk about isothermal. This will be really good in the physics lecture, by the way. This will make a lot more sense in the physics section. But basically, isothermal means that the temperature of the system is staying constant. So there is, let me write that in like red or blue. I just used red, so let's use blue. So there's no change in volume. Adiabatic. This one's a hard one. I'll actually go back to that because these two are pretty easy. Isovolumetric. So that means based off of what we know about isothermal, it will be Oh my god, I'm so sorry. I wrote delta V here. Isothermal is iso. Is a no change in temperature. Isovolumetric is no change in volume. I'm so sorry about that, guys. Isobaric. This isn't like, it's a bit harder, but I think like as people who've taken science classes, you guys know what it's about. No change in pressure. Now let's go on to adiabatic. What do you guys think that is? Right, no heat exchange. So no delta H, I guess? No change in heat. Or no heat exchange. I'm just gonna write it like that. I don't want to confuse you guys. With that being said, endothermic, exothermic, like I said, we talked about that. Q equals MCAT. Do I have anything written at the bottom of this? I don't, so we can talk about that. So Q equals MCAT, that's just the equation you need to know. If you're ever stuck with like a calorimetry question, know that this is specific mass. This is I said specific mass, I'm sorry, but specific heat. This is mass. I don't think I need to label that, it's pretty obvious. This is the heat that you're looking for. And delta T is change in temperature. So, what's your question about that exactly? Where would I apply? But yeah, it's for calorimetry. So, processes? I'm not entirely sure why I had this written. But state functions, let's look at that. State functions, it is basically all the important like properties that you can think of. So it's like pressure, I just wrote like a capital P, but like a lowercase p would be density. I'll just write density for you guys here. Pressure, density, temperature. What else are you guys thinking about? Volume, and the ones you guys aren't, I don't see anyone writing in chat, is enthalpy, entropy, it gives free energy. And we're going to talk about that in just a second. So let's move on down here. So enthalpy, enthalpy is always the hardest one for me. So if you guys have questions, feel free to ask. We can go in depth about this. Just know that it's just the heat of formation. It's basically what heat change is. So basically standard heat of formation this is one that you guys need to know. This basically products minus reactants. And delta H reaction would be, oh, I'm so sorry. No, that's it's the other way around. Sorry, guys. Yeah, no, this is why I hate enthalpy. It's delta H reactants minus delta H products. I'm moving like up for this. I'm not. It's weird. Yeah, like I said, I'll calibrate this after stream. Hopefully the biochem will be a lot smoother. Reactants minus delta H products. Delta H of reaction. Now that is products minus reactions. I'm so confused. Yeah, I know. I feel that. I'm thinking because like I don't want to just make you guys watch a Khan Academy video about enthalpy, because like it's kind of the point of here what you're being here. So like, what is enthalpy? Is the exchange of heat in a system. It's basically the way I'd like to think about this is that enthalpy, you don't really have to know what it is or what it's about. You just need to know that when a question is given to you about enthalpy, they'll probably give you a chart about the heats of reactions and formations. You can just plug and chug, know the equations, and I can't say you plug and chug. This is the MCAT. You're never going to be plugging and chugging. Analyze what you have given to you in the passage and the question stem, and if you know these equations, you should be solid. Now, moving from the hardest one, let's move to the easiest one, entropy. It's the disorder that's present in the universe, as everything is just expanding outwards. So just know that a positive entropy is usually preferred. Usually always preferred. One of the few constants in the world. Wow, that's so embarrassing. So I'd like to say that with that being said, the delta S of the universe would be of the system plus its surroundings. See that this is one of the few ones where you have a plus. So this would be going, I'll write this a bit smaller just so I don't mesh in with delta G. But yeah, like I said, this has a positive attached to it. And this is one of the few ones that are like that. Usually you always have like negatives going with these thermochemistry equations. That being said, that's why this is the easiest. It's the easiest to remember that this will be positive. It's going out. Trying to think, is there anything else I can say about delta S? Not really. It's pretty straightforward. So yeah, I think that's all you guys need to know really. Delta G, we've talked about it a lot, but we don't know exactly what it is. It's the free energy that is present, and it combines enthalpy and entropy. It creates like a functional equation. So this is the equation for it. Delta G equals delta H minus T delta S. Excuse me. So when we have a positive delta G, what does that mean? It means that it's not a spontaneous reaction. Non-spontaneous. That means we have a negative value for this. Or we have a negative value, or like we have a very positive value for enthalpy. And if enthalpy is larger than entropy, it's not preferred. That's not what the universe wants. It's hard for this reaction to move forward. You're going to have to use a catalyst. It's going to be very difficult to get it up and going. Now, a negative delta G, what does that mean? Well, knowing what I just said, this is a spontaneous reaction. Negative delta G means that it's a high entropy, low enthalpy, it's going outwards, it's easy for the reaction to move forward. Most natural reactions are non-spontaneous negative delta G reactions. So make sure you guys know that. That's basically it. I think, well, if delta G equals 0, it's equilibrium. You'll never see that in a MCAT question. You'll never make it that easy for you. It's always going to be a question of it's spontaneous or non-spontaneous. Temperature does play a role though, so I think I should have written this in a better way. Don't worry, we'll think about it. So let's say we have a low delta H. There's low delta H, but we have high temperature. What does that mean? Or not low, let's say positive or negative. Yeah, you're right. I was thinking negative, positive. So that means, yeah, it will be spontaneous at every temperature because the delta H will be preferred. So what about if they're both positive? Well, let's think about it. So if it's positive here and it's positive here, if delta T was 1 and they both have the same value, you're basically canceling each other out. So you're going to need to create a very high temperature, or at the very least, something high enough to cancel this out. So if these are positive, you need to have high temperature. Now let's move on to negatives. So if delta H is negative and delta S is negative, what does that mean? Same logic, guys. So if this is a low, if this is negative and this is negative, you need something that's decreased for it to create a spontaneous reaction. All of this is trying to create a negative delta G, by the way. And if this is positive and this is negative, then it's non-spontaneous all around. Cool. I think that's basically it. Yeah, sorry. I wish I had a better chart to show you guys. You guys know the chart I'm talking about. It has like all the stuff written like in the sides. It's basically telling you what it's all about. But this works too. If not, feel free to look in your books. I'm pretty sure Kaplan has a chart for this. Princeton Review definitely has a chart. Blueprint, they all have charts. So yeah, this I think thermochemistry that took up an entire thing. Oh boy, gas laws. Before we get started on gases though, let's take a small break. I'll get back to you guys in 4 minutes, 3 minutes, 4 minutes. What are you guys feeling? I'll say 4 minutes. I'll see you guys soon. I just realized that I probably, like, whenever I take a break or I call for a break, I should probably write that, like, we're on a break or something. Because if someone ever comes in, I'm sorry. If someone ever comes in and they see that, like, it's just like an empty chair and it's like a bunch of stuff that isn't written, and they probably think like it ended or like I haven't started the stream or whatever. But yeah, no, I'll make sure I do that in the next stream. Gas laws. Who's ready for gas laws? Yeah, no, don't worry, buddy. I hate gas laws too. No, I'm kidding. This is really important. This is important stuff. It's very interesting. It helps you understand chemistry and physics, if that makes sense. So we'll just be talking about it. It's nothing super like intense. I think if you know the gas law, you'll understand the relationship. So first off, let's talk about standard temperature pressure. I'd want to, like, before I start off with the gas law, start off with standard temperature pressure. So STP. What is that? When or where is it? Like, what are the... So let's talk about pressure. Let's talk about temperature. Let's talk about... Well, yeah, those is standard temperature pressure. Volume, it shouldn't matter with the STP. So for temperature, it'll be 273 Kelvin, which is also 0 degrees Celsius. I was thinking about adding something about like Fahrenheit, Celsius, Kelvin, but like I've done so many like practice problems. I've talked to so many students who've done practice problems. They've never had one that talked about like converting from Fahrenheit to Kelvin to Celsius or whatever. It's always Kelvin to Celsius, or vice versa. Just know that Kelvin is Celsius plus 273. For pressure, it's 1 atm. And note that I want more space. So 1 atm equals 760 milligrams, or millimeters of Hg equals yeah. We'll talk about all of that. Hold your questions for a second. 760 torr, and it's like that's about, I don't want to say it's equal to, but it's about 100,000 Pascal. Oh, that looks like 100 kilopascals. I'm so sorry. 100,000 Pascal. Obviously, you can do the conversion for kilopascals, but yeah. So with that being said, let's dive right into the ideal gas law. P equals nRT, pivot. We all know that, right? Like that's the one equation that's always stuck in our heads. So how do real gases act? Because this is the ideal gas law. What are real gases? How do they act? So let's talk about this. So change in pressure. So an increase in pressure will cause what? It'll cause the particles of the gas, it'll cause it to come closer, right? So increase in pressure will lead to a decrease in the volume. But if you have, but at high pressure, at moderately high pressure, what happens there? Right, yeah. So at moderately high pressure, it'll just be slightly less. The MCAT likes testing that because like they're saying like that moderately high pressure, that's where the preferred ideal would be, but it's getting slightly less. So that's where it starts changing. So when you start changing the temperature, what happens then? So decrease in temperature also causes a decrease in volume. Why is that? It's because the kinetic energy of the molecules starts to decrease with the decrease in temperature. So they all start coming closer together. They don't occupy as much space. Now at very, very low temperatures, what happens there? Wrong. Wrong. No, it actually isn't a very lower volume, but it's actually increasing the volume, slightly more than it's preferred. It's because they have to occupy a space that like where they can't condense. They don't want to condense or also start forming liquids. They'll start forming solids. So they occupy a space that's slightly larger. So I want you guys to know that. It's a bit weird. I won't lie. Yeah, real gases are a bit weird because they don't like conform to what you think they are. Like we give you a law and then they change it because of reality. That's just chemistry though, right? Every single thing, if there's an exception and they only test you on exceptions, it's annoying. But hey, what can I do? I don't make the exam. I just teach it. So, Boyle's law. It is PV equals P2 V2. Now note, actually I'll circle the constants later. But yeah, PV equals P2 V2. They have a relationship with each other. An increase in P1 or an increase in pressure will lead obviously to a decrease in volume, right? Because you want to maintain the equilibrium here. So with that being said, let's move on to Charles' law, which is V over T equals V2 over T2. Now, if you increase V, what happens to T? You increase it, right? You have to increase it so you can maintain whatever you have going on here. Avogadro's law. So, I should have written Gay-Lussac's law actually, but I'll write it somewhere else here. Avogadro's law states that moles over volume is also directly proportional to each other. So, likewise, if you increase that, you also have to increase that to maintain that. Gay-Lussac's law, I'll just write it here. It's a bit small, but pressure over temperature equals pressure over temperature 2. So, same reaction. And now let's combine all of them together, guys. That's Boyle's law. Now that's Charles' law and Gay-Lussac's law over temperature equals P2 V2 over T2. I would like there's like you could add what is it? You could add N. It'll be a bit more complicated though, but like you have Pivners for that if you want. So that being said, we've talked about the variations so far, how to manipulate it, all the relationships. You can figure this out. If you increase P, obviously you have to increase T, but you'll be decreasing V just to maintain equilibrium, vice versa, stuff like that. Now, with that being said, I want to hammer into your heads, there we go, that these, they're all constants. That's why you have to keep changing them. Now that came off really weird. Hang on, let me explain that. They're constants. Like this PV number, it's going to be a constant. That's why if you increase the pressure, you have to decrease the volume to reach that constant. It's same thing with N over V, P over T, V over T. This also as well, because like I said, if they're all constants, you have to make constants. That came out really weird. Sorry about that. But yeah, is there anything else? I think we're moving forward here. There's some partial pressure stuff I wanted to talk about. All right, let's go. Partial pressure. It's basically like, this is total pressure, and that's basically the sum of all the partial pressures. So think of it like PA plus PB plus PC. Unfortunately, we'll never get something as easy as that on the exam. So I think you need to think of it more like PT is chi A. X over XA is basically moles of gas A over, yeah, you were right, sorry, total moles. Yeah, so yeah, basically this is a bit more like, I'd say this is basically the more important equation. I think the only thing that's left to cover is kinetic molecular theory. It's pretty like obvious, I guess, because like, we all know kinetic energy is 1/2 mv squared, right? So obviously, like if you're increasing the mass, you got to decrease the volume by a lot. Vice versa. One thing I'd like to point is that you can derive this to create a different one called 3/2 times K. It's a constant times the temperature. This is the average speed of molecules. With that being said, I think that's everything I can cover here. Let's move forward towards phases. This is, I like phases. An easier one we can talk about. I love this chart because you can't get it wrong. It's very easy once you understand what's going on, guys. So, solid, liquid, gas. Solid, liquid, gas. I don't know how you guys want to memorize this, but just a solid, liquid, gas. What else do I want to talk about here? Triple points and critical points. I'll get to that. I'm just trying to see if there's anything specific I want to talk about with this chart. Note that the slope, this slope right here for water or H2O, will be negative for the solid phase, which is seen as like a really big deal for chemists, I guess, because water is one of the few molecules that has it like that. Like most of it's usually positive. But yeah, other than that, I guess we can just go right into triple points and critical point. I'll talk about triple point first. Triple points, that's where everything meets up. Critical point, that's where the temperature and pressure of a gas reach a point where they start expressing properties of both. They created something that's called a supercritical fluid. Now, this is almost always going to be a discrete question. I've never seen this on like any passage, but it's going to be discrete. It's going to be relatively simple. Just know which one. Just know your charts. And if you do see this in a passage, remember solid, liquid, gas. Solid, liquid, gas. Now, let's talk about... Do I want to move forward to this phase diagram, or should I go to colligative properties? I'll do colligative properties. So freezing point, depression, and burning. Freezing point, depression. Freezing point, depression, boiling point, elevation. So, does anyone know the reaction to this? It's like that. And then freezing point, depression. Now, I don't really... I'm trying to think, because like you never really see like a conceptual question about boiling point elevation or freezing point depression. It's mostly you have to find, like if you give the question stem or in a passage, you're just trying to use this equation to solve for something. So basically, this is something that you just need to know. Trying to make it look more like an E. Yeah, this is something that you need to know. Moving forward, let's talk about osmotic pressure. That's the important colligative property I want to talk about because this ties into biology, biochemistry, physics. This is very important. So osmotic pressure equals I MRT. I should have explained these. So like the I is the Van 't Hoff factor. It's basically just like if you're given any reaction, it's basically the coefficient of whatever you're talking about. So these are constants, the boiling constant, freezing constant, these are masses. This is temperature, this is molarity, Van 't Hoff factor. I want to state that the osmotic pressure is important because it's the pressure that's like you need to prevent osmosis from happening. So like I want to think osmotic pressure is not correlated or like directly proportional to osmolarity. It's inverse. So yeah, I talked about everything else. I think we can move straight forward to this one. I think it's important to know the concept of changing phases. So let's move back to, I've been using a lot of red. Let's go to blue. Actually, no, I'll stick with red. So from this point right here, you see that you're just staying as a solid. The temperature is increasing, but there is no change going on. You're still a solid. But then, perfect, I can use both colors now. Once you reach the threshold, you start melting. This is for water, by the way. Once you reach the melting point, you start melting. The temperature of the compound does not change. You're not absorbing any more or you are absorbing heat, but you're not you're not gaining more temperature in the object. So then afterwards you move forward to the liquid. Here you stay the same. Nothing is inherently changing, no properties, nothing like that. That's really weird. Yeah, there we go, that's a lot better. And you're moving all the way up. Once you hit the boiling point, you start evaporating. And then after that, plasma, or gas, sorry. I was about to say, like, we all know the fourth one is, the fourth phase is plasma, but you'll never be tested on that. They don't talk about plasma in like the chemical or physical sense. They always talk about plasma in the biological sense. So if you ever like really want to think about plasma, think about what's going on in your blood. Well, yeah, with that being said, let's move forward with Graham's law. It's diffusion versus effusion. Diffusion is when your gas molecules move through a volume. So I'm trying to think of a better way to say it. Diffusion, effusion. Okay, here's a good idea. That was horrible. Gas moves. Diffusion is when you enter. A new. I'm thinking in like a box. You enter a new environment, and the gas is diffusing throughout it uniformly. Effusion, on the other hand, it's more like you're forcing the gas molecules out. It's being forced out of the environment. So I don't want to put new here because the gas moves uniformly in the environment when it's being diffused. Effusion, it's being forced out. So gas moves out of environment. And it's always like usually in like a very small like hole. So like here's like the thing I have going on in my head right now. I'll explain it to you guys. If this is the box and like I'll make it like more like a traditional box. Yeah, that's something, but all right. So if you guys have like a box and like let's say there's like a little hole in the box right here. So like I'll draw like a little hole and we have a bunch of molecules in here, right? A bunch of gas molecules. Now they're all like evenly distributed out here, right? But because we know how equilibrium works, we know how the universe works, you always want to go from a high concentration gradient to a low concentration gradient. So what does that mean? These diffuse molecules, the ones that are all like universally distributed, they effuse out towards the box or the other box where there is no molecule. So they start being forced out. They'll be effusing. If it's a small hole, it will be effusing at a rapid rate. If it's a larger hole, it will be a bit slower. Or sorry, other way around. Because like if it's a small one, you're not going to be able to fit as many molecules out. But yeah, that's basically what diffusion and effusion is. I think I just wanted to throw it in there because it's something that a lot of students struggle with. Equation, yeah, I'll add the equation too, don't worry. So the effusion and effusion rates, so it's R1, which is rate of diffusion, R2, rate of effusion. Or they have they're both, my bad, equals M2 over M1. M2 over M will obviously be masses. So with that being said, let's move on to acids and bases. We're almost done, guys. Don't worry. Acids and bases. Where do I start with you guys? I could have sworn I put salt solutions here. Did I not? Or did I skip it? Solutions is next. Okay. Acids and bases. So with acids and bases, let's talk about definitions. I want to talk about Arrhenius, Bronsted-Lowry, and Lewis. So can somebody give me like Arrhenius acids? They're the easy one. Yeah, okay, sure. So these are the ones that have either an H plus or an OH. These are easy to tell because they have either one. Now, Bronsted, Lowry, and Lewis, these are the ones that are a bit tricky because I've gotten them messed up. I don't want you guys getting them messed up. So, Bronsted, Lowry, they still have these. What's the difference? An acid, so I'll write it later, but an acid would be a proton or a hydronium donor, while a base will be an OH acceptor. Now, you can think about it like, you have an Arrhenius acid, you can also have a Bronsted-Lowry acid. They could be the same, but like, you need to think like operationally. In a question, they will ask you like, which one of these is a Bronsted-Lowry acid? Like yeah, sure, it's an Arrhenius acid, but it can also be a Bronsted-Lowry acid, or vice versa. Now, the Lewis acid, you're not thinking of hydronium or hydroxide, you're thinking of electrons. Now, if you're donating a proton, you're also going to have to accept an electron. So Lewis acids are electron acceptors, while Lewis bases are electron donors. Acid base, acid base, acid base. Just make sure we know that, guys. Now let's move on to pH. pH is essentially describing to us what the products, or not the products, the properties of an acid or a base is. So pH, we know the equation. It's negative log H plus. Right, guys? Right. Now POH, negative log OH. Now, well, these work together hand in hand, right? So you want to make sure that they all add up to 14. This is a standard one. In theory, you can go higher than 14. You can go lower than 0, but most likely you won't. I'll just say that. Like this, like the higher than 14, lower than 0, like that's for like a science class, not for the MCAT. Now, if we're thinking, oh, it's right here. I'll talk about KW here, okay? So Ka is the constant, as the acid constant. So Ka equals I want to know that, like, looking at this equation, how would you know if an acid is a strong acid or a weak acid based off of Ka? Let's talk about it. A strong acid is determined on how much of a hydrogen or how much hydronium ions you have. So the more hydronium you have, the stronger your pH, or the lower your pH is. Now, what does that mean? If your lower pH is more acidic, stronger acid. So you want a strong Pa, or increase in Ka, increase in strength. Now, it's the same thought process when it comes to Kb, which is the base constant. But that is instead OH times whatever base you have, conjugate base, Hb. And now I was talking to you guys about Kw, which is the constant of water. And that's basically just concentration of this, concentration of that. It equals, it's also just basically Ka times Kb. I've seen a lot of discrete questions about this, like it's asking you like what Kb would be given Kw and Ka. So you can just manipulate it. So like Kw or Kb would be just Ka or Kw over Ka. I also want to state that Kw is also 14. I'll just write it. I don't want to be weird about it. Kw equals 14. So, yeah, this is for weak acids and bases. For strong acids and bases, you can obviously just go off of like whatever the pH is, or finding out whatever the concentration of the protons are, or the OH. But like with this, with weak acids, you're going to need that. Amphoteric species, they can work as either acids or bases. That's another vocab term you guys should know. I don't think there's anything else I can really talk to you guys about acids and the bases. Let's just move on to titrations. Now, titrations, we know how it is. We've all been in a chemistry lab. You basically you just drop the base, right? You drop the base into the basic solution into an acid solution. Works with the phenolphthalein or whatever indicator you have. It reaches a certain point, and then it'll change color to be like hot pink. But there are different like indicators. I'm not entirely sure how important it is to know them for the MCAT. I think if you have free time, you can look it up. But just know that phenolphthalein is the main one. You're trying to get it to be around 8 for it to change. Yeah, so with that being said, let's look into this. At strong acid, strong base, it's a pretty straightforward graph. Or if it's red, I should probably just choose blue. Yeah, there we go. It's a strong acid and a weak base. You're adding in a weak base, right? So you're starting off at 2, but you're ending at around 9. You're not adding, your pH will not be changing that much. There will be a very little change. So that's how you can tell if it's a strong acid or weak base. Weak acid and weak base. Like I said, not that much change. It's a more gradual change. It's going up, but it's not, you're not going to have, it's still a low, pH. I'll say like just slightly basic. Now, weak acid and strong base, this is the closest you're going to, 3 is still pretty acidic, but like this is the highest you're ever going to see it, so slightly acidic. And you're going up, it's going to be very basic here. So just note that if you have a strong base, you're going to see something up here. Weak base, you're going to see something down here. Henderson-Hasselbalch, it's easy for you to find out the equation for something, or the pH of a compound. It's used specifically for like buffers. So if you have a buffer and you need to find the pH of whatever that buffer is to see if it's like a good buffer, because like we know how buffers work. It's essentially you have to, if it has to be, or I'll write it down for you guys. A good buffer is within 1. I'll write it as this. It's plus or minus 1 of the pH of the solution. Now, Henderson-Hasselbalch, it's kind of a complicated equation, especially since we're adding in logs. But I would say that for like almost every single MCAT question, you don't have to worry about this part. pH would just basically just be pKa. pKa is correlated to Ka. pKa is just negative log of Ka. I'll write that up top, I guess. Yeah, basically ties into this. With that being said, here is a really ghetto chart that I made to talk about like pKa's. This was basically, they'll give you pKa's and you'll be able to tell which one is which. A higher pKa obviously means that it's more acidic. So, but these are something that you need to understand or need to memorize. Because if they ask you which one has a higher pKa, HF or HCl, followed by like 2 like throwaway answers, you need to know what HCl has a higher pKa and it's more acidic. So yeah, just memorize this, I guess. NaOH, it's like we know that one. We use it in our chemical labs for titrations. It's the typical one. It's very basic. I think these two right here. These two right here, they're the scariest ones. Just make sure you memorize that HCl is more acidic than HF. With that being said, we are on. Oh no, you thought we are on our second to last one, which would be solutions. So, solutions. I'll talk about the vocab terms first. I'm trying to I'll give myself some space here, and then we'll go back to specific rules. So molarity, we know what that is. It's just moles over liters. It's something that we've always been working with since like the dawn of time. Molality is a bit different though. That is the moles of the solute we have over liters of the solution. Why do we, like, what's the significance of this? I'd say that it's mostly like passage based or like question based. If they're asking you for molality, you need to know what it is, what they're asking for. Normality is like, it plays into equivalence. So it's like number of equivalents over liters of solution, usually given to you in grams. So this would be in grams. Mostly vocab terms. I don't really, this is like very low yield stuff, but it's still, I wouldn't say low yield, sorry. It's more like, it's just, it will show up on the exam. It's probably going to be like 1 or 2 discretes. You'll like, I don't think it gets screwed over in a passage if you don't know what this is. That being said, let's move on to our solubility rules. This is like, I've seen this in my like high school textbooks. You've probably seen this in yours too. I don't have any fun ways to memorize this, unfortunately. All my like mnemonics are like in biology or like psychology. I'm sorry, I don't have any funny chem ones. Yeah, no, I'm sorry guys. You're just gonna have to memorize this. If there's anything I can say to like take away from this, is that calcium, it's written right here. These guys are just not soluble. You're not going to be able to dissolve them. So yeah, with that being said, let's move on to our final topic. Redox and electrochemistry. Now, I'll start off with redox first. Oil rig. There it is. I have a mnemonic. Oil rig. What does it stand for, guys? We all know this one. So oxidation is loss. Oh, that's so lame. Hang on, I'll write it like vertically. Oxidation is loss. Reduction is gain of electrons. So with that being said, let's talk about redox. It's mostly straightforward. I'm basically just going through like vocabulary, because vocabulary is very, very important with oxidation. Because like, if you think like just knowing oil rig, you're probably not going to be able to do well. Because like you need to think about like oxidizing agents. I'm trying to like use my space well. Oxidizing agents, reducing agents. So let's talk about that. Oxidizing agents are agents that are able to cause another atom to oxidize. So these oxidize others. Therefore, they get reduced. Now, using that logic, reducing agents, they reduce others, right? Therefore, they get oxidized. It's like really like, you need, I struggle with this a lot. I went through so many different problems getting it wrong. Even when I thought I got it I got it cold, I wouldn't think, and I'd always get it wrong. So even if you think you understand this, make sure you know it cold. That being said, let's move on to electrochemistry. Electrochemistry is pretty hard, but I still like it anyways because it's just a personal interest of mine, I guess. Galvanic and voltaic cells. Before I get into these, let's talk about another cool mnemonic I have: anox, and red cat. I'll make it right very quick, actually. Anox, red cat. So, anox, oxidation. Oxidation occurs at the anode. Reduction occurs at the cathode. That's a universal right there. So let's make sure we have that hammered into our heads. All right? Now, with that being said, let's move on to galvanic cells, also known as voltaic cells. Are considered to be like our traditional cells, where we have like oxidation occurring. The transfer electrons will be going from here to the cathode. So electron flow, I'd like to point out, electron flow is anode to cathode. But current flow, because we have a current, we have something that has to facilitate this. In this case, it'll be a cell bridge. With an electrolytic cell, we have an actual like battery. It's cathode to anode. So yeah. If you want to find the E cell of an equation, it's also cathode minus anode. I'll write that. It's here, but I think I'll write it bigger just for you guys. Cat minus E anode. You see it right here. It says that galvanic cell must be negative and it must be spontaneous. The E cell of a galvanic cell is greater than 0. I'll talk about it right here in a second. I'll go over this in a second. Electrolytic cells, they're basically the opposite, I want to say, because I mean it still flows like this, but it's still like it works essentially like in the opposite directions, if that makes sense. Because it's non-spontaneous. Yeah, it is non-spontaneous. Why is it in one container? That's just how electrolytic cells work. Now, let's move on to EMF and delta G. Let's wrap this up really quick, guys. EMF, honestly, right here, it's the same as E cell. EMF equals E cell. It's the reduction potential at the cathode minus the reduction potential at the anode. Let's talk about reduction potentials for a second really quick. Reduction potentials, it's basically like this stuff right here. They'll be given to you in a chart. They'll give it to you, and you have to know that the higher a reduction potential is, the more likely it is for it to be reduced. The lower it is, the more likely it is to be oxidized. And note that if they give you oxidation potentials, it's essentially just the inverse of reduction potential. So like if something has, I'll just keep it in blue. So like if the reduction potential for something is like, say 70.70, its oxidation potential will be negative 0.70, and vice versa. And now let's wrap things up with how we relate all of this to Gibbs free energy. So the equation for this when it comes to electrochemistry is negative F E cell. E cell, we have it here. We can just plug it in. N is the number of reactants. or not reactive, it's just number of species present. And F is known as Faraday's constant. You guys will be learning about that a little bit more in physics, but just know that for the sake of the constant, it's about 100,000. The real value is like 96,400, something like that, but like, for the sake of plugging things in, I don't want to do too much math, just 100,000, that's more than enough. With that being said, that covers basically everything for chemistry. Yeah, we did a lot of writing, guys. Yeah, so that being said, I did say we'll cover some math. I want to see if we have time for that. I don't want to like overwhelm you guys. Yeah, we got time, don't worry. Let's cover some math. I'm gonna move like a bit further, like here. Let's do some math. So multiplication, division, I think that's pretty easy. Scientific notation, you guys aren't struggling with that, I'm assuming. I don't even think that, like, do you guys understand the right-hand rule, right? Like, I can cover that in physics in more detail, but it's basically like the direction of the vectors, and it's like wherever, like, if A is going this way, B is going this way, C is either like wherever your palm is going. Yeah, I know, we can talk about that in physics. Let's talk about logs then. This is very important, I agree. So like, I think that multiplying logarithms, it's log A times log B is basically the equivalent of adding them together. And dividing logs, so like log A over B, is subtracting. This one's an annoying one. So like raising a log to the power, so log A to the power of B. You basically, it's like, if you're familiar with calculus, it's similar to like taking a derivative. B log A. That's basically how it works. And if you have like the inverse of a log, so like log like 1 over A, it's basically negative log A. Wow, this is basically just gonna be all logs. I'm trying to think of something else. Natural logs, let's talk about that. So like natural logs, like if you have log X, you can just convert to a natural log by doing ln X times 2.303. Sorry, I'm thinking of the base equation first. So like then you bring it up here. So like natural log X is actually just log X times 2.303. Just double it. And no, I'd rather just like guesstimate it. And I think this is the most important equation. So like log n times 10 to the m would be like m plus 0.n. Not exactly, but like sort of. What other questions do you guys have about math? Sine, cosines, tangents, stuff like that? Nothing? Cool. I'm glad I don't have to talk about that much math. I still think there's some stuff. We can hang out for a little bit longer. You guys want to talk about mode, mean, and range? Probability? Let's talk about probability, because I know like people are going to struggle with probability. So the probability of, let's talk about like mutually exclusive and independent events. So mutually exclusive means that two events can't happen together, while independent means that the probability of A happening is not dependent on probability of B. So for now, I'm going to be talking about the probability, assuming it's independent. So the probability of A and B happening would be probability of A times probability of B. So like probability of me like landing a head and rolling a 6 on a die, that would be like 1/2 times 1/6, right? They don't like, they have no correlation with each other. They have no connection. Like if just because I get a head doesn't mean I automatically get a 6 or whatever. So with that being said, that'll be a 1/12 chance of getting both. Probability of either of them happening, probability A or B, that would be something more like P A plus PB minus P A and B. I'm not entirely sure of the statistical reasoning behind this, but like it doesn't matter. You just need to know the equation for this. So we can just, if we're using the coin and die analysis, let's talk about it. 1/2 plus 1/6 minus, we just saw that 1/12. So 1/6 minus 1/12, that's 1/12. 1/2 minus 1/12. So let's do 6/2 or 6/12. It's 1/12. 5/12. Any other questions you guys have? What is standard deviation? Don't worry about it, man. You don't have to solve for standard deviation. Just know that it's like if you have a mean, so like, this is a poor way to think about it, but like, let's say the mean is 7, and then the average is 7, and then the next standard deviation, so like the next like tick mark, basically, the spread, it's basically like 7, so this is like 5, let's say it's 3, 9, 11. This would be the next significant place. So like within one deviation of each other, we know that 68% will be in this area. 2, it'll be 95%. It's basically a measure of like how many people are there, if it makes sense. So like if you have the mean, that's the 50th percentile, right? But then if you have one standard deviation above, you're hitting 50, well, you'll be hitting like 68th percentile. Not 68th percentile, sorry, you'll be hitting like somewhere in the 70s. Because you have to be adding 68, like whatever, like the 68 here, and then the area here. No, I'm sorry. You'll never be asked a question like this. It's just like whatever is like in the higher or lower standard deviation, stuff like that. With that being said, any other questions? Vectors? We'll talk about them in physics, man. Alright, well, if you guys have any other questions, I believe that's all I have for you guys. So, yeah, we covered a lot of stuff today. Tomorrow, I'm going to hit you guys with like a mega lecture of organic chemistry, physics, and biochem. It's gonna be a long one. We're gonna be here a while tomorrow. Organic chemistry and physics aren't that bad. They won't take up too much time, but biochem, it's gonna be a doozy. But that being said, I hope you guys were able to learn something here. I hope you guys are preparing for the exam. I wish you guys good luck, and I wish you guys a good night.